Yeah, okay. Okay, so for this case, you use the inductive hypothesis. Then n equal to n minus 1 plus 1, that will be just 1 plus big O. Will again be big O. So this kind of proofs are false. Never use induction along with this big O notation. Okay, you should always expand this. So what this means is n is at most some constant c, and then start using induction. Okay. So last class in integer multiplication, I showed you this recurrence Tn equal to 4Tn by 2 plus n. Okay, and I think we saw the solution also, which was order of n square. So let's say you make a bad guess. We say that Tn is order of n cube. Okay, so assume that Tn is at most some c times n cube for some constant c. Then you will also need to show that 4 times Tn by 2 plus n. This is also at most some constant times n cube. Okay. So substitute n by 2 in this. What you get is 4 times Cn cube by 8 plus n. This will be Cn cube by 2 plus n is also at most Cn. Okay. So this is obviously true because Cn cube by 2 is always larger than n. Why is that the case? If you put C any constant to be larger than 2, it will be n cube is always larger than n, which is obviously true for any n larger than n. Right? So what this tells you that Tn equal to order of n cube is always a solution to this. Okay? But we don't know exactly which function it is. Tn is big O of n. Okay? So now we use a smaller guess. Let's say Tn is at most Cn square. Okay. Then you substitute in this 4Tn by 2 plus n. So when you substitute 4Tn by 2 plus n, this will become 4Cn square by 4 plus n. Is at most Cn square. That's what we want to prove here. But this is obviously false. Cn square, this will become Cn square plus n, and on the right hand side you have Cn square. Okay. And since n is positive, this quantity will always be larger than Cn square. So does this imply that Tn is this Tn equal to order of n square is false? Is not a solution to this?
Yes, sir.
No, because the problem here is that you are picking Tn equal to at most Cn square. Okay. But the thing is that there could be some linear terms also, linear terms and constant terms. Right? So if Tn is big O of n square, don't assume that Tn is at most some constant times n square. Okay. So it could be of this form also. Tn is at most C1 n square minus C2 n. Okay. And now we want to show that 4Tn by 2 plus n is at most this quantity, C1n square minus C2. So we substitute this in the right hand side. So what we get is 4C1n square by 4 minus 2C2n plus n. And we want to show that this is at most C1n square minus C2n. So the first term gets cancelled out, C1n square, C1n square. And for any C2 larger than 1, this quantity will always be less than this minus C2. Right? For any C2 larger than 1. Right? For any C2 larger than n, 4C1n square by 4 minus 2C2n plus n is at most C1n square minus C2. So this is an example of the substitution method for solving recurrences. And similarly, you can argue that Tn is at least C1n square minus C2 using this very recursion. Okay. And that you can check for yourself. So this is another example of a recursion. Tn equal to n square plus Tn by 2 plus Tn by 4. So here we'll use another method which is known as the recursion tree method. So corresponding to this equation, we draw some tree. Okay. And let's say this tree has at most 10 leaves. Okay. We assume that this tree has at most 10 leaves. In this t n by 2 will have at most n by 2 leaves. This n by 4 will have at most n by 4 leaves. So n by 2 plus n by 4, that is some 3n by 4, that is at most n. Right? By induction, you can show that number of leaves is at most n. So at the initial level, we have that this overhead term is n square. Okay. At first level, what will be the overhead term? N over 2 square plus n over 4 square. Okay. So this will be n square by 4 plus n square by 16. 5 by 16 n square. So now at the second level, what will be the overhead term? Someone calculate and tell me. So the first level was what? You expand this Tn by 2, right? So here you will get n by 2 whole square plus Tn by 4 plus Tn by 8. Okay. Then you expand this Tn by 4. What will get n by 4 whole square. So initially we had n by 2 whole square and n by 4 whole square. So that we summed up and we got 5 by 16 n square. Similarly, now you have to do the same for the second. Yeah. So initially you understood, right? At the zeroth level, there is this n squared term. At the first level, what do we get? Expand this Tn by 2, expand this Tn by 4. When you expanded this Tn by 2, n over 2 whole square, that is n square by 4. When you expanded this Tn by 4, you get n by 4 whole square, that is n square by 16. And then when you added n square by 4 plus n square by 16, okay, why is number of leaves at most n? So in this tree, we have this Tn at the top. Then we write Tn by 2, Tn by 4, and n square as the overhead term. And then you keep on expanding this tree. Okay. So by you'll use induction here. We claim that the number of leaves is at most 10. Then you look at the smaller terms, Tn by 2 and Tn by 4. Here you assume that the number of leaves is at most n by 2. Here you assume the number of leaves is at most n by 4. So the total number of leaves will be n by 2 plus n by 4. Right? 3n by 4, which is number of leaves is at most n. So the tree is not that much important. What I want to see is the overhead term. Okay? So if you have calculated this, it will become 25 by 256 n square. And you sum up all these terms. So what special do you see about this series? Yeah, got squared, right? And you take any recursion, it will always be a nice series. So what do we call this series? These are geometric series. And you should be able to sum this, right? So what is the sum up to infinity of this series? A by 1 minus C. Yeah, that is the formula. So it will be 1 over 1 minus 5 by 16, right? So that is some 16 by 11. Yeah,
Yes,
16 by
yes.
11. Got it, got it. Okay. So overall, this summation will be at most 16 by 11 n square, right? So the solution of this recurrence will be order of n square. Okay, so this is a very intuitive way of solving this recursion.
Sir,
Yeah,
sir, in using this method, we can only find order of the solution, not the exact solution, right?
yeah, we don't care about the exact solution for now. For exact solution, you have to use the previous method, substitution method.
Yeah. Okay, sir.
Okay,
Thank you.
okay, yeah. Because we in computer science, we just care about what is big O of what solution, right? We are not doing exact mathematics here. And if you need a proper theorem like statement, I want to apply this theorem and solve this recurrence. So then we have something called as master theorem, but it only works for a specific kind of recurrences. Okay? So it looks like this, Tn equal to Atn by B plus f of n, right? If you have more terms, then you can't apply this theorem. But if you just want something to remember and solve the recurrence, then you can use this theorem. So the idea is that they compare this n term Fn with n to the power log b by a. So this is the total number of leaves in the recurrence tree. Okay. And then you say that Fn is smaller than this term, then Tn will have the solution theta of n to the power log b by a. If it is equal to this term n to the log p by a up to some polylog factors. Okay. So if you have a log n power k multiplicative factor of this, then the solution will be this much log n to the power k plus. Okay, theta of n to the power log p by a log n to the power k plus. And if Fn grows bigger than this n to the power log p by, then this Fn factor will dominate to Tn. Right? Tn equal to theta of Fn will be the solution. So let us apply this Master's theorem here. Tn equal to 4Tn by 2. So here b equal to 2, a equal to 4. Right? So n to the power log p by n will be n square. And in this case, this term is much smaller than n square. So the final solution will be Tn is theta n square. Right? So this is what master theorem. So we'll see some more examples now. I'll stop sharing this. Okay, so now we'll solve this recurrence using recursion tree method. Let's say I give you this recurrence Tn equal to 3Tn by 4 plus 3 theta of n square. So how will you solve using the recursion tree method? By the master theorem, the solution is clear because n to the power log 4 by 3 is dominated by n square. So n square will be the solution. So how will you draw the tree here? So Tn breaks into Tn by 4, Tn by 4, Tn by 4, and there is a Cn square over. Then again this Tn by 4, you substitute in this equation. What you'll get is 3Tn by 16 plus theta n by 4 whole square. So we have this Cn by 4 whole square, Cn by 4 whole square, Cn by 4 whole square. And there are three terms of Tn by 16, n by 16, n by 16. So this is how the overall tree looks like. Okay, so initially we had Cn square. Then we broke down into Cn square by 16, Cn square by 16, Cn square by 16. So this gave us 3 by 16 Cn square. Again, this tree broke down into Cn by 16 whole square, n by 16 whole square, n by 16 whole square, and so on. So it gave us 9 by 256 Cn square. Okay. Again, it's some kind of geometric series. And how long will this tree grow? So every time we are dividing by 4, right? And when this tree uh, stops growing, when n becomes equal to 1, right? So you keep on dividing by 4. When does n become equal to 1? It is log n to the base 4. So this is the total height of the tree, log n to the base 4 plus 1. And finally, you'll get T1, T1, T1. Let's say it's some constant. Okay. And then just sum up all this stuff. Cn square, 3 by 16 Cn square, 3 by 16 whole square Cn square. And how much will this sum be at most equal to? Again, it's geometric series. And if you evaluate, it is 1 over 1 minus 3 by 16. Right? 16 by 13 we get. So it is at most 16 by 13 Cn square. So the total solution will be order of n square. Right, so the tree method is very intuitive and you don't have to remember anything to solve recurrences using this recursion tree method. Now try to solve this example. Tn equal to Tn by 3 plus T2n by 3 plus Cn. Here you can't apply master method because there are two different recurrences running in parallel. So you have to use recursion tree. Yeah, order of n log n. Somebody got it. Okay. So how did you solve it? So we wrote it as Cn. In the first step, we get Cn. Right? So when you evaluate T of n by 3 using this formula, you'll get Cn by 3 and there will be some Tn over 9 and T2n by 9. Right? So from this step, you will get C times 2n by 3. And then you sum both these up, you will again get C. So this should be Cn over 9, C2n over 9, C2n over 9, C4n over 9. So if you sum up all these terms, you'll always get Cn. And how large is this tree going to grow? So there are two different trees going on here. This tree is going to grow much slower, like 2n by 3, 4n by 9. So overall log 3 by 2 to the power n. Okay? And this tree will take log n to the base 3. And overall growth will be, and at every level you add Cn term. Cn, Cn, Cn. For how many levels? Log n to the base 3. Therefore, the solution is Cn now. Okay. You can verify for yourself that many of you got as well. So yeah, so this requires a lot of practice. I have just done a few examples here. And the more you practice, the more you will get experience with this method. Otherwise, you can always use that master method and apply the formula and get the answer. Okay, if there are any questions, we are happy to answer. So these are some asymptotic notation. Can you see why 2n square is log of n cube?
Sir, because for C is equals to 2, 2n square is always less than 2n cube for n more than 1.
Yes. Yeah, that's correct. I think this is wrong. So now there are some more examples. 5n square plus 3n is big omega of n square. Again, you can choose c equal to 5 here and it is larger than 1. So yeah, I have just taken some examples here, but practice as much as you can so as to be very comfortable with these definitions. Okay. Yeah, if there are any questions, let me know.
Sir, I am having a question.
Yeah.
Sir, here in solving recurrences, our goal is to basically find the upper or lower bound of the function in question, right?
Yes, yes.
Means we need not find the exact solution of that function.
Yeah, because usually when you are finding out the running time, different devices will have different hardware capabilities. And
Yes,
right? So,
yeah,
they'll take different running times. And we just want to bound the total number of time taken on any device. So that is
uh,
why we are, yeah,
yes, sir, understood, sir.
right? So
Thanks,
that,
thanks.
so that is why we are not going for exact solution. If you want the exact solution, you can use that substitution method, but then you have to make the right guess and it is difficult to solve recurrences exactly. So that is why we are just looking at approximate solution.
Hello, sir. I have a doubt.
Yeah,
Sir, in that, how height came log n?
which one?
That Tn by 3 plus T2n by 3 plus Cn.
Yeah, let me check.
Yes. No, this.
No, this one. No.
No.
Here.
Hmm.
So what is happening over here? At every step, you are doing this Tn by 3, T2n by 3. So in this,
Yes.
at every step, height is get then in the next level, you have divided by 3 every time, right? So this becomes n over 3, n over 9, then n over 27, and so on,
Hmm.
right?
Yes.
Now, at what value will this become equal to 1? So it will be some 3 power k equal to n. So at the kth level, it will become equal to 1,
Yes.
right? So what is that k? That is log n to the base 3,
Yes.
right? And this tree, it is growing much slower because here it's 2n by 3, then 4n by 3, and uh, so it is getting divided by 3 over 2 every time. So in this
Hmm.
case, you get log n to the base 3 by 2.
Okay.
Okay,
I got it. Thank you, sir.
okay. So yeah, this will take some practice. Get used to it so that you can solve any recurrence. Are there any more questions?
No, sir.
Yeah, okay. Okay, then we'll stop this meeting for now. Meet on Monday, 8:30.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Hello,
May-
sir.
That file also.
Okay.
Yeah, sure.
Hello, sir.
Yes.
Sir, will you share PPT on email or we have to join a Google Classroom or Moodle or something?
I will share on email.
Okay, sir. Thank you.
Okay.